Hello, everybody. Good afternoon or good morning, depending on where you are, and welcome to this session, Civil Engineering and Renewable Energy 4, Mr. Gary Littler from UCD. So, Gary, feel free to turn on your camera and share your screen.
Full cheers. Share screen. Cool. Hi, everyone, and thanks for attending. I'm Gary, and I'm a master's student at UCD. My presentation is on developing seabed scour assessment and prediction tools using computational fluid dynamics modeling, or the demo project. And a little bit about the outline. I'll start off with a little bit about renewable energy, move on to scour, what is it and why does it matter, and a bit about the demo project itself. So our methods, the study area chosen, the modeling plan, and some possible advanced modeling. So I'm sure you've all heard of the Paris Agreement. Everybody's trying to meet carbon neutral targets, and a big part of that is renewable energy. So around the UK and Ireland, we're very, very suited, and there's massive investment to offshore renewables. And in this talk, it'll be about specifically offshore wind power. Now, you can see on the right-hand side there, there's that's the Arklow wind farm, the only actual existing structure in Ireland. That's a two-stage project, and stage one was completed about 2004, and they're hoping to have the second stage up and producing electricity by 2025. So what is scour? Scour occurs when shear stress on the bed is exceed the frictional and rotational forces that are actually holding the grains in place, governed by the Shields parameter, a dimensionless number there, as you can see on the right-hand side. And if you leave it alone, something like this can happen. This is actually shortly after the installation of a monopile at Arklow. So if you leave that alone, I'm sure you can imagine the catastrophe that could occur with destabilization of the structure or possible toppling. So companies have to invest heavily in time and money to actually fill it back in, and then proceed to try and mitigate the issue with defenses like rock armor, but that might not solve the problem. So it's useful to actually have a prediction model in place, and that's where the demo project comes in. It's part of the Geological Survey of Ireland's research programme. That's where funding came from. And we're trying to ask, what is the range of scour development in the Irish Sea? What formation processes are involved in influencing parameters? And our goals are to use CFD to model the areas of excess shear stress around a proxy object chosen. In our case, it's going to be a shipwreck. To validate the model, comparing it to real-world observations, adapt the model to apply to monopile turbines and possibly other structures, and to explore other possibilities to improve the robustness of the model or its accuracy or applications. Now, the data that we actually gathered is from a number of GSI and Marine Institute projects. So the SCOPE project involving ICRAG and GDG, the GIST survey led by ICRAG again, and the morphodynamic study of the Irish Sea project funded through the Marine Institute and involving again GDG and ICRAG. So bathymetry, what is it? Basically, bathymetry is it's a picture of the seabed, so taken from a measuring device on board a moving platform. So either an acoustic echo sound or LiDAR. LiDAR is brilliant for shallow water, obviously being light based, pretty useless for deep water. So ours was all gathered from on board a ship. You saw the two ships earlier of the Marine Institute, the Celtic Voyager and the Celtic Explorer. So here's a lovely example actually showing exactly what they do. They're going and taking transect after transect and zigzagging back and forth until they get nowadays quite a high resolution representation of the seabed and what's on it. And you can actually view a lot of this on the Infomar website. I would definitely suggest going and taking a look. Shipwrecks, pipelines, drop-offs at the shelf. It's some really nice stuff. And there you can see the sort of level of detail you can expect in a 3D model from the information, excuse me, the information available. So what area did we choose? What rec did we use? We had a few different recs to choose from, but we based our criteria on somewhere close to where a monopile might actually be installed. So the company standards and availability of data, obviously, we needed to have repeat surveys. In the case of the one that we chose, it's the SS Powell. We have 3 years full of data for the likes of the current vector magnitude and such. We wanted it to be clear of marine protected areas and shipping lanes. So you can see here, that's Dublin there. So it's north to east of here, so it's not directly outside the mouth. It needed to be in a reasonable substrate. So you're not going to go and try and put this in rock. Just not viable at all. And it needed to be less than the cutoff depth for a monopile turbine of around 50 meters. Beyond that, you've got to use a floating platform. So, and it's close to proposed installations. You can just sort of see at the top of here, that's the top of Arklow Bank, to give you a reference over where that's actually at. And this, I think, is a very nice representation to show you the direction you can imagine of the current paired with a rose diagram here, and that's current frequency. So our initial modeling plan, that'll be a RANS simulation based on a paper by Quinn and Smith. We're using an idealized surface for the seabed, so a roughness will be applied to that. It's a simplified approach, and we just find where the high areas of shear stress are actually at. So we've got the inlet and that outlet will be patch type, slip condition on the top wall down the bottom, and symmetry either side. So the solver to use is pimple foam because it's a large step transient solver, obviously for compressible flow, and can solve for turbulent flows. And we'll be using the K epsilon turbulence model. The initial velocity will be 0.147 meters per second based on an average of the 3 years current velocities. So, and water will be represented at 10 degrees based on assigning a kinematic viscosity of 1.307 based on the previous paper mentioned. So that's the actual resolution. We've got the Powell there. That's 20 centimeters resolution. So you can see there's actually quite a high level of detail we're working with here. So it's a joy to work with, to be honest. That's the initial boundary area we've got at the moment. So 100 meters by 100 meters and 25 meters up. The Powell is actually 29 meters deep, but as the sea surface is at a dynamic and changing area due to waves and currents and that, it's useful, I think, to have a buffer in between. So to verify our model, we'll run a mesh sensitivity study, and we'll be testing also different domain sizes to ensure there's no boundary effects, and obviously making it the smallest possible without any adverse effects. Validating, we're going to, like I said earlier, we're going to compare it to real world data, the repeat surveys, and then switch the wreck out and the seabed for one or the other was a possibility, and see if it can stand up to that change. Once that's been verified and validated, we can then model a monopile turbine, or we could extend that if we want beyond that to rock armor, cables, pipelines, a monkey's head, whatever you want to throw down there, to be awfully honest. And advanced modeling. Now, we haven't had a large discussion about this yet, but instead of using an idealized surface, using a sediment transport model to more accurately measure the volume sediment moved based on obviously the grain size and etc., I think would really improve the model, provided everything obviously goes all right. This is still early stages. We're about 6 months through, so hopefully that's where we'll be moving in the end. And that is the end of my talk. Thank you very much for listening. And if you have any questions or suggestions, absolutely.
Great. Thanks very much, Gary. Very interesting talk. If people have questions, feel free to type them into the chat. Yeah, I have a few questions looking at it. Well, first of all, some comments. It looks like the data set is really nice, really rich data set. How much? What format does this experimental data come in?
It comes in, well, it can come in a variety, but you usually bring it down to like a shape file. But the actual ship itself and the geometry was a point cloud format.
And how do you? So do you use Snappy Hex Mesh then to mesh your domain around the?
Yeah. Sorry, I'm using Snappy Hex Mesh to get that taken off.
How do you go from your point cloud to an STL?
The point cloud, I went through Blender actually. Big shout out to Yusuf Naj.
Very good. Very nice. And how large are these meshes? You mentioned about mesh sensitivity, and I know this is a project it's still ongoing, but are you ending up with very large amounts of cells?
You know, I've not been that far with it, but I think the last measurement of a cell when I was just starting to increase size was about 18 million. So
okay.
Yeah.
They're going to take some time to run these, so you'll need you'll probably need to use one of the clusters available to you or something like that.
Oh yeah, definitely the HPC cluster is going to be a large part of this.
Can I ask you a little bit about the sediment transport? So you've identified this sediment transport approaches, maybe the one that will be most suitable. Has that been implemented in OpenFOAM? Do you know?
No, I don't know that yet. I would definitely like to actually look into that further. At the moment, I've just sort of taken everything step by step. Sure. As I'm like, I have no real history in fluid dynamics or anything, so it's all a learning experience.
Okay, perfect. That's great then. I don't have any more questions, so thanks very much for a nice talk, Gary.
Cheers.